So first, I have a confession to make, which is I noticed there are some errors in the entanglement entropy formula I gave you last time. So here's what I ought to have written. That part's the same. This part's the same. But, so I said that I and J are the transverse indices that are parallel to the surface, and A, B are the normal ones, like that. And whenever I wrote the curvature tensor, it should have been the normal ones and not the transverse directions. Was copying it from a source where the convention was the other way around. So this term should be like this. And this term, I made the same mistake and I forgot to put the integral sign. And then the rest of this is as it should have been. Okay? So that's the correct thing, but if you don't want to believe me, you can look it up in a nice paper by Forsayev, Petrushev, and Solodukin, where they work this out, or everything except the m-squared piece from the quadratic curvature action and the replica trick. Also, at least one person had the impression that I was making some claim that this dimensional analysis of the entanglement entropy was something that people haven't discussed. It's something people have discussed quite a bit. 90% of what I was telling you was just common knowledge. The thing I was saying people don't usually emphasize is that there's also a universal piece of the finite term in even dimensions. I think that's it for the previous lecture, unless there are questions about that. Oh, and if there's the presentation of this argument will probably be cleaned up, and if there are any mistakes corrected in the paper I eventually write with Will Donnelly about universality that should be coming out in the next couple months. So if you want a definitive source for that argument, it should be located in the future. So if there's no questions about the previous lecture, I will proceed to talk about holographic entanglement entropy. All right, gonna erase this. So we're discussing now ADS-CFT. So to review this, because the limits are kind of important, we have a duality that is believed to be exact, that is between strings or M-theory on a space-time that looks like ADS d plus 1 times some compact fiber. Because string theory lives in 10 dimensions and M theory lives in 11 dimensions, So you need a fiber space to bring the dimensions up to the right total. And this is supposed to be dual to a CFT in d dimensions. That's little d for the CFT dimensions. And then we can take a limit that's called the holographic limit, where on this side we take LADS to be much greater than L Planck, which is the same as saying that G Newton's constant goes to 0. And we also sometimes take the limit where the LADS is greater than the string scale as well, which and so the first thing corresponds to large n, where n is the number of fields, and the second thing corresponds to a strong coupling limit, where the coupling doesn't necessarily go all the way to infinity, because in many of these theories there's a S duality that makes it weak coupled, but it goes to some strong coupling. So the reason I've put this one in parentheses is because the string theory has a string coupling constant and M theory does not. So the versions of this duality that involve string theory typically involve going to strong coupling, but the ones that involve M theory, typically you don't have a weakly coupled version of the theory in the first place. So there's sort of only one holographic parameter in this limit. So once you've done this, you get the supergravity limit on this side. So this is a classical local theory that's just GR coupled to other things. And on this side of this commuting square, we have the holographic limit of the CFT. So people sometimes refer to the CFT in the holographic limit as a holographic CFT, but if this thing is really true at the level of string theory or quantum gravity, then when we expect it to hold even for sort of regular CFTs that are far from the holographic limit. Almost all of the known examples of this duality involve string theory or M theory, but I would believe that if your favorite theory of quantum gravity, if you're a loops person somehow and you somehow manage to get your theory to work, I would think it would still have some holographic dual if you put it in ADS spacetime. There was some interesting work by Alex Maloney and some other people where they looked at putative holographic duals to very low central charge CFTs and related it to things like pure 3D gravity and other theories. So that was a very interesting paper that I will not describe. Okay, so this is our setup. And now we will discuss the Ryutaki-Yanagi formula. So the formula is true. So this describes the leading, that is classical, and the sort of supergravity limit piece of the entanglement entropy. And this version of the formula applies only to a static situation, or more generally, you could consider a moment of time reversal invariant slice, sigma, of the space-time. So we confine attention to one moment of space-time where the past is related to the future by Z2 symmetry, the same situation that usually you need if you want to Wick rotate, although that also requires analyticity, and this doesn't. Okay, the next point is people usually ignore F, but you don't have to. That's the fiber direction up there. So usually people just talk about surfaces in ADS space-time. They're implicitly assuming that the fiber dimension is just constant throughout the ADS. But if it's not constant, you can still define this in 10 or 11 dimensions. And so what you do, the construction, is that you find the minimal area surface. So I'm drawing space at one time here. So this is sigma. We have a region, R, and it has a boundary. And now we look for the minimum area surface that's anchored to this boundary, subject to a further constraint called the homology constraint that I will tell you about in just a moment. And we can now write at the entropy of R is equal to the minimum over all possible curves that we could write down that are anchored to this point of the area of that curve in units of 4gh bar, and whatever is the solution to that, I will label as MR. Okay, so this guy is the von Neumann entropy we've been discussing before, restricted to the region. And this is gamma is restricted to be a codimension 2 surface in M, which means it has to be codimension 1 in sigma. And the rules are it has to be anchored to the boundary. And actually that follows from a stronger constraint. It has to be homologous to R. So let me just say a little bit about this homology constraint. It generally arises in situations where there's something topologically non-trivial about the space-time. So let's take, for example, the Penrose diagram of the eternal black hole. So here's the Penrose diagram, and a not-so-Penrose-y diagram looks like this. And one special case we can consider of, you might notice that this looks a lot like the Bekenstein-Hawking entropy of a black hole. And indeed, in this case, it's going to reduce to the Bekenstein-Hawking entropy, which is the area of a minimal surface that's along this moment of time symmetry. And that corresponds to the case where we take our boundary to be all of one of these CFTs. And then our anchoring, since there's no boundary of R, the rule now is that we're looking for a surface that isn't anchored to the boundary. So it should be a compact surface that's somewhere in this space-time. So there is a compact surface in this space-time that's here, the minimum area surface here, and its area over 4gh bar gives the black hole entropy, and it also gives the this holographic entanglement entropy of the CFT on this side. But this is a situation where you need to impose the homology constraint, which means that the surface has to separate the region from its complementary region. Because otherwise, there's another surface that has even less entropy that is compact. Does anybody know what that surface is? Go on, I can't hear you. Somebody bold. What surface has less area than this one? It's so simple you aren't even thinking about it, like thinking 0 isn't a number. It's the empty set, yes. So the empty set has less area than this surface, but it's not an allowed candidate for the holographic entanglement entropy because it would not be, you couldn't continuously deform it to the region R. So it's not homologous to R. And this arises in more complicated settings where you have, for example, a black hole and you take some region on the boundary. Then you will have to make sure that the region R properly separates if I took a surface like that, this would not be homologous because there's a black hole here. I'd need another connected component of that that's here. And then the sum of this and this is homologous to R. Because you can deform it in such a way that separates R from R bar, where here R bar is what's on is not only this, but also what's on the other side of this black hole. Okay, so that's the homology constraint and is crucially important for defining this. Now let me give some examples of how this works in some specific holographic CFTs that are the ones most commonly discussed. So I'm going to show you some examples in 2, 3, 4, and 6. So the bulk, and there's a strongly coupled, here's the entropy at strong coupling, and here's the entropy at weak coupling, which is outside the holographic limit. So the classic case is n equals 4 super Yang mills. I didn't have a column. I meant to have a column for the CFT. So the classic case is n equals 4 super Yang mills in 4 dimensions, where confusingly we have 2 n's. For people who have not previously been hazed by this theory, there's 2 n's in this theory. There's the curly n, which is the number of supersymmetries, and there's the not curly n, which is the gauge group. So this is dual to ADS5 times S5 in type 2b string theory. And the entanglement entropy that you get from working out what G Newton is in this theory corresponds to n squared. And the same thing is true. This theory has can be continuously adjusted to weak coupling because of supersymmetry, and it also has an entropy of n squared. There's a similar thing that arises in 2 dimensions called the D1, D5 CFT, and this is dual to ADS3 times S3 times T4 on the 2B theory. And this one, the n, the thing that plays the role of the n, is the central charge, and that's also the same. Yes, it's also the same at weak and strong coupling. And so in these cases, you have C and CA are protected by supersymmetry so that they have to have the same values at weak and strong coupling. Any questions about that?
Isn't there those 4/3 discrepancy between weak and strong?
Yes, but this is supposed to be in order.
Just
This is not supposed to, I'm not putting in the numerical coefficient. But that's correct. So some examples that are a little bit different are the examples you get from compactifying M theory in ADS4 cross S7 or ADS7 cross S4. So this one's dual to what's called the ABJM model, where you start with a weakly coupled theory with order n squared fields that are coupled to a Chern-Simons field in the UV, but then you let it flow to the IR, and you get in the holographic limit, the entropy is not the same as in the weakly coupled theory. It's n to the 3/2. Similarly, if you do it this other way, you get what's called the 2, 0 model. That's amazingly quantum field, a CFT that exists in 6 dimensions, which you would never have guessed by thinking about perturbative quantum field theory that this thing could exist. And in this case, the flow goes the opposite direction. In the UV, it's the strongly coupled theory, and somewhat surprisingly, this has an entropy that's proportional to n cubed, which sort of defies our field theory expectations, and it flows in the IR to constructions that involve super Yang mills that have n squared degrees of freedom. So you can see the number of degrees of freedom is decreasing under the RG flow, so that makes sense. And you can also see that these guys have a n to the d over 2 structure here. Okay, so why am I giving you this chart? And I should say all of these entropies here they're subject to, this is just the leading order effect, so there's also in a 1 over g, coming from a 1 over g expansion, there's also plus order 1 corrections. And these were described by, for example, Faulkner, Lugwitz, and Maldacena. So this protection of the central charge at weak and strong coupling is part of the initial evidence that showed us that this thing was likely correct. So one important point I haven't mentioned so far, this area functional is divergent. So we have to put in a cutoff, a UV cutoff epsilon, to cut off this UV divergence here. I probably should have mentioned that before. And so to put in this cutoff, it's not completely clear how you should do it because none of the field theory cutoffs I mentioned, except possibly the mutual information one I think you could do, most of them don't have an obvious application to the bulk side of the holographic duality. Instead, we do something else, usually, which is with respect to our holographic coordinates, r or z or whatever you want to call it, you just put a cutoff at fixed like z equals constant. And when you put in this cutoff, it's just a geometrical dividing line, and then you only measure the area up to that thing. And then you can see how it scales with taking that cutoff that plays the role of epsilon in my previous lecture to 0. Now, this is where the discussion of universality becomes important, because this is a different cutoff than the cutoff we had most naturally put in the field theory. So if I want to compare to a field theory result, then I need to look at a universal term. So historically, one of the first checks of this was that the log divergent terms associated with these central charges were the same in the supergravity theory with these minimal area surfaces as they are in the corresponding field theories at weak coupling. Since the holographic theory is at strong coupling, an important part of that is that these central charges are protected when you flow from weak to strong coupling. Does that make sense? So the evidence for this or consistency conditions, there was the universal pieces, I mean here the evidence for Ryu-Takeyanagi, not the evidence for ADS-CFT in general, for which, of course, this is just one of several parts. The second kind of evidence is certain the consistency properties, like all of the inequalities I mentioned earlier, involve things like strong subadditivity. So quantum information inequalities. Like strong subadditivity. And the third major piece of evidence, which is almost a proof, is path integral arguments. Using the replica trick. And so this is the Lukowitz-Maldacena method that's been generalized by many people. Okay, so in this lecture, I'm going to be focusing on, I'm going to try to get to talking about strong subadditivity. And in the next one, hopefully I'll have time to tell you about this path integral method. All right, any questions about this? The next topic is phase transitions. All right, so by the way, if you want a homework problem for holographic entanglement entropy, there's a very obvious one, which is to pick a region in the boundary and to actually calculate for the ADS metric the minimal area surface that is associated with that region. Now, since there are people in this audience with many different skill levels, the beautiful thing about this homework assignment is that it scales in difficulty. So you can decide whether your dimension should be bigger and how much symmetry your surface of the region should have, right? Depending on whether you're a grad student or a postdoc or faculty. So, but if you are a grad student, one thing you should bear in mind if you choose to do this exercise is that you should remember that minimization is a kind of action principle, and that action principles are far more easily solved by using Noetherian conserved quantity methods than by just working out the equations of motion and trying to solve it directly. Okay, so one thing that will happen for certain choices of regions in space-times is that there might be multiple local minima. So when you have multiple local minima, so one example of this that arises in pure ADS is if I consider two disjoint intervals. So I could just consider a sphere, for example, and I could pick some angle theta. And for simplicity, we could consider this angle to be the same on both sides. And now I can define my define regions A and B here. So since there's 4 points here, if I were in D equals 2, then there's 4 points here, so there's one conformally invariant cross ratio here. That's can't be transformed away with a conformal transformation. So there's two phases here. So what we can consider is the entropy of AB. So one phase arises when the angle theta is small. When the angle theta is small, then the minimum, there's sort of two candidates for the minimum area surface, because we could connect it either like that, or we could connect it like that. So if theta is small, we connect it like that, and then we find the SAB equals SA plus SB. And that tells us that the mutual information is actually 0 up to, all of this is up to order unity corrections that arise from quantum effects that require you to add a bulk entanglement entropy term to this. So, whereas in the other phase, where it connects like this, if I take A and B separately, they're still disconnected. So then I find the SAB is less than SA plus SB, and therefore IAB is of order n squared. Well, not n squared if I'm in 2 dimensions, but of order whatever it should be in this chart. We could call it of order 1 over g, and then it'll be true in every dimension. So if I plot as a function of theta the entropy of this as theta ranges from 0 to, I guess it only makes sense to take it to pi over 2, then what we'll find is that for a small interval, there's a log divergence that makes the entropy go to, the entropy looks like it's going to minus infinity as the radius goes to 0. Now you might worry about that because entropies are supposed to be positive. But I'm plotting this holding epsilon constant. So it goes negative when the region is smaller than the size of the cutoff, which doesn't really make sense. So we have the log divergence here. And then on the other side, in the case of d equals 2, so that there's one space dimension, this is actually symmetric under flipping this chart horizontally. So the same thing happens on the other side. And so what you have is you have 2 separate possible branches. And when we do the global minimization, you pick whichever branch has the least entropy. So that would be given by this curve here. And what you'll notice about this is it means that my entropy as a function of theta, the parameters in the problem, actually has a phase transition. It flops between these 2 phases, and S is not itself discontinuous, but the first derivative of S is discontinuous at this phase transition. So that has a sort of a picture to sort of justify this, you can relate it to the fact that in, say, n equals 4 super Yang mills, there's strings, and there's a sort of difference between whether, if your region is, if you have a long interval, then you have long strings, and your region breaks the strings up into pieces, and you get order n squared effects. But if you have short intervals, if it's like this phase, then the sort of Rindler thermal, Unruh thermal excited strings are just form bound states, and you just have order 1 information. It's closely connected to the Hawking page phase transition, where at high temperature, well, so at low temperature in the CFT, your ADS is just filled with quanta, and in the n equals 4 super Yang mills, those just look like quarks that form various color neutral states, and so your entropy is of order 1. But at high temperature, you have a black hole, and that corresponds to a deconfined quark gluon plasma whose entropy is of order, say, n squared in n equals 4 super Yang mills. But the same kind of phase transition also can happen with one interval if you have a black hole, where you can see that as I grow this region on the boundary, if the region is small, my homologous surface is going to be like this. But if the region gets big enough, then it's going to flop to the union of the curve that goes round and the black hole itself. You can see that in the limit where this becomes small, like if it were a small region on the other side, then it would certainly be better to have the black hole plus the small interval. So, and this doesn't even require a black hole. If you just have a massive star here, you can also have phase transitions. Okay, so that's something to watch out for. Are there any questions about this before I discuss strong subadditivity? I felt I need to discuss phase transitions because they often come in the discussion of strong subadditivity for various regions. I'm going to erase this. Yes?
Is there some sense in which you would expect that the approximations that go into this prescription would break down?
Yeah, I was going to mention that. So phase transitions usually happen when there's some sort of infinity in the problem. They don't happen in a finite size system, is sort of a standard thermodynamic result. I mean, they don't happen at the mathematical level, although in practice, even once a system gets even a little bit large, you see it experimentally. And so in the same way, if you're doing this chart, the phase transition here is expected to only exist at infinite n. So if you're at finite n, the expectation is that this will be smoothed out a little bit. That was your question? Great. So the question, well, FLM have done some work on what are the quantum corrections if you're on one side or another. I actually think there's still some mysteries and paradoxes and puzzles associated with how you should take into account these quantum corrections if you're right at this phase transition. and there's sort of two rival Ryuta-Yanagi surfaces that are competing. I feel like when you get close enough, it should be sort of a quantum mechanical matter. There should be some contribution from both of them, or it should be quantum mechanically uncertain somehow which ones you use. And if they're equal, it's tempting to adjust it by a factor of plus log 2 for the entropy of not knowing which one it is. But to make this smooth out, looks like you should have a negative thing instead. So I think it's puzzling. Was there another question back there?
If you have a star in the wall, do the Hrt surfaces probe the interior before the phase transition?
In general, no. The phase transition stops you from probing the interior. There's going to be a region that no Hrt surfaces. For a sufficiently massive star, for any star whose mass I hold fixed, and then I take the limit that the ADS length becomes large. In that regime, the phase transition always happens. And when there's such a phase transition, you typically get an entanglement shadow, which is a region that is not probed by any Ryuta-Yanagi surfaces. So while when you're close to ADS, there are these results that you can work out the Einstein equation from things like the linearized Einstein equation from the first law of entanglement on the boundary. And so you can sort of derive the bulk equations of motion from Ryuta-Yanagi. But when you are far from ADS and you have this entanglement shadow, it's clear that there's a region that cannot be reconstructed from Ryuta-Yanagi alone. So maybe you have to think about tensor networks or complexity or some other horrible thing. Yes?
Repeat your argument about when we consider the 1/n corrections, what is the puzzle exactly about the...
Oh, so I'm just saying so we know that at finite n, this phase transition is smooth out. And so as a simple example, you could consider the case where it's symmetrical and we have two surfaces of exactly equal area. And because it's symmetrical, even like the FLM corrections will be equal. And the question is, what happens right when they're equal? So you might have thought that the answer is that you need so whatever happens should smooth it out. But right at the middle, to see how this function is different, you might have thought there should be an extra, like add log 2 or something, from the qubit or the bit uncertainty as to which of the two surfaces you have. But in fact, if you can see that if you smooth this out, the function should go down, not up. So maybe it's minus log 2 or something weird like that. Or maybe it's something completely different. Okay. If there are no other questions, yes?
Can you explain again? In the hot phase transition, so what is the role of the temperature?
Right. So the point is that when you have intervals, you have an Unruh effect. And when you have an Unruh effect, there's a temperature. And it sort of depends on how big the intervals are. So when you have a small enough region, it's as if there were... So in this... Sorry, I think I didn't explain this diagram well. Let me do it again. I want this to be my two regions, A and B. And so the statement is that for a small interval, it's hot, and therefore it looks like there's a bunch of strings, and they're like open strings that end on the boundary, and they have some sort of quarks. It looks like a quark gluon plasma. But for a big interval, you should think of the strings as effectively as if they have some characteristic length once you turn on the temperature. And so if the regions are far away, it's like you're in the cold phase. And if no string is going to be long enough to produce non-trivial order n squared entanglement between A and B. But if they're close, there can be strings that cross all the way over for both of them that provide some sort of order n squared. Okay. So it's sort of a question of whether you could like segregate the information, this extra region, so that it's the mutual information is order 1 or order n squared. So you might have thought that this would not be a sharp phase transition, but in the large n limit, it becomes sharp because there's infinitely many degrees of freedom. So you can have a situation where if I just increase the temperature infinitesimally, there's suddenly a lot more degrees of freedom, which can't happen at finite n. Okay, so let's discuss strong subadditivity. I'll do it here. Okay, this chalk isn't any good. So one nice thing about this Ryu-Takanagi surface, as pointed out by Hedrick and Takanagi, is that it automatically obeys strong subadditivity. So that's actually something that's very difficult to prove from quantum information, although it is proven. So it's interesting that geometrically, it has a very simple proof when you do holographic entanglement entropy. So there's a sort of a picture proof. So I'm going to consider the case I did at the end of my previous lecture, where we have 3 adjoining intervals, A, B, and C. So, and I'm going to let this be the holographic dimension. So the minimal area surface that joins A and B looks like this. And the minimum area surface that joins B and C looks like this. And the minimum area one that joins B looks like this. And then there's one that goes up above like this. So the statement of strong subadditivity is that SAB plus SBC is greater than or equal to S, the union, plus the intersection. That's one of the 2 forms. You can prove both of the 2 forms this way, but let's focus on this one. So the proof is very simple. You observe the fact that where AB and BC, where MAB and MBC cross, you can choose to reconnect the surfaces. So instead of taking this sum to be this surface plus this surface, I can take it to be this yellow surface plus this, that looks kind of similar. I'll do blue. It's this blue surface. Can everyone see this? Now, by reconnecting the surfaces, I didn't change the area. But now, I can compare this yellow surface to this one. And since MABC is by definition the global minimum of all possible surfaces anchored to the boundary of ABC, this yellow surface has more area. Similarly, this blue surface is going to have more area than MB. Therefore, I prove this inequality. If I choose to reconnect the surfaces in the other direction, I would get the alternative form of strong subadditivity. So There's also a more complicated inequality that can be proven by similar methods. The monogamy of mutual information inequality that says SAB plus SBC plus SCA is greater than or equal to the sum of all the ones plus all three. There's a similar proof of this by reconnecting, but I won't try to draw it on the board. The principles are exactly the same. In fact, with the work of Ning Bao and others on the holographic entanglement entropy cone, I'm sorry I don't remember all of his collaborators, they found an infinite series of inequalities that can be proven for static Ryutakiyanagi by this method. However, strong subadditivity has an important difference from monogamy of mutual information, which is this one is a true quantum information theory inequality that is true for arbitrary density matrices and Hilbert spaces. This one is a special case for holographic spacetimes that is not true for general states. Like, for example, this is violated by the GHZ state. And the same, I think, seems to holds for these more complicated things. Okay. So that's a nice consistency check. Yes.
Does this proof depend on the details of how you're implementing the regulator on it?
So good question. So you'll notice I was being coy about the regulator, and the regulator is important for in the same way I said at the end of my last lecture about strong subadditivity, that if you have a situation where, so in this situation, you can show that the divergences all cancel in the case of the simple case of three intervals right next to each other. And the way you show this is by noting, so you might worry that these ones have different divergences from each other. But you can prove they don't, because if one of them was more divergent than the other, then it would be more efficient at a certain point to jump over to the one with less divergences, and that would minimize the area even of the other one. Does that make sense? Like if this yellow one was more divergent, then that would say there's a surface of less, that this surface that looks like that would have less area than the yellow one, but that's a contradiction. So in this simple sort of situation, you can show that the divergences cancel. However, as a more general matter, you can also find situations like these disks that I talked about where the divergences don't cancel, and you only find something out about the whatever is the leading order divergence that doesn't cancel. So if that happens to be a universal divergence, like in the log divergence in 2 + 1, you've still learned something interesting about the dual theory. If it turns out to be a non-universal divergence, then this proof of strong subadditivity is not as interesting, because it just tells you about the holographic regulator of the strong subadditivity. Of course, we already knew field theory did satisfy strong subadditivity if you use, say, the lattice regulator. So this is more interesting because it tells us something about GR in space-time and how it must, GR knows about quantum information, so that's how the it comes from. Somehow this is a clue about how the it comes from the qubit. Yes?
So yeah, but GHC that state were violating monogamy like of mutual information, but that kind of implies that GHC that kind of structural state will not be able to have a holographic field.
Right, so there is no way to write a normal holographic space that will give rise to 3 regions that have the GHZ type structure of their entanglement. That's correct. Therefore, there are states that are not dual to a good classical space-time, at least of the usual sort. Of course, we knew that anyway, because there can be things like there are states in the, you shouldn't think that every state in the CFT is dual to a classical geometry, even in this holographic limit that I erased, because you could, for example, have a state that's a quantum superposition of 2 very different geometries, like a quantum superposition between a black hole and a neutron star. That's going to be described by a quantum superposition of geometries. Yeah?
Do you think the basis of states in CFT being geometries, classical geometries?
Probably it's really an over-complete basis. That is, most likely you can find situations where there's multiple ways to interpret, like one geometry might be a superposition of other geometries. Like, for example, there's a nice paper by Dan Jaffris about this recently. For example, if you consider this thermofield double state, then that will have a non-zero inner product with the 2 copies of the ADS vacuum, because that's part of the thermofield double. It's a small overlap, so the inner product is very close to being 0, but it's not entirely 0. Other questions? Questions are better than me just telling you things that may or may not answer your question. So don't be shy. Okay. So actually, I think I'll go. So now I'm going to talk about what happens. So this was very restrictive, that we could only talk about holographic entanglement entropy in this static context. So there's a generalization of the formula, which is the covariant generalization, which is called the Hrt formula, where the H is Hubani, the R is a different R, it's Regamani, and the T is the same T, Takiyanagi. So how do we change this story? So first of all, I need to change my picture to include the time dimension. So now we have a region on the boundary, but my entropy should be the same, should really be a property of the domain of dependence here. Okay. And what we do now is we want to look for a codimension 2 surface that sticks out into the boundary and is anchored to the boundary region. So this one works for time-dependent manifolds, or even in the static case, you need to use it if the region is time-dependent. Like if I have some boosted, if I have like 2 intervals and I boost one of them relative to the other, then time plays a role. So the formula is now going to be that, so you could say, well, look for a minimum area surface in the space-time. But that's never going to be correct because the space-time has Lorentzian signature. And so if I make a very wiggly, if I wiggle this surface in time, it's always going to decrease the area because of the minus sign in the metric. So I can never just minimize the area. Instead, I have to extremize the area I have to extremize the area to get M of R, and that means that I demand that its first order variation has to be 0. Make sense? But this is the analog of saying I have a local minimum in the Euclidean signature. So in general, there may be a phase transition where there's multiple candidates for there's multiple extremal surfaces that are both anchored to the boundary and are in the same, and are in the, are homologous to R. So in general, if there happen to be multiple candidates, I also have to minimize over that typically discrete set of candidates. Okay? So this is the Hrt formula. All of this other stuff is basically the same. So this extremization is equivalent to saying I demand that the trace of the extrinsic curvature, so the trace of the extrinsic curvature tracing over these transverse indices, I demand that that be 0. And that says that this is an extremal surface. The mathematicians call out the extrinsic curvature the second fundamental form, but I'm talking to physicists here. So, okay, so now the question is, can we still prove things like strong subadditivity? And it's not obvious, because if you remember this proof, we used global minimization as part of this proof. So the extremization condition says that it's just extremal, and that it's only minimum compared to any other extremal surface, but not compared to some non-extremal surface. So from what we have so far, it's not going to be obvious whether strong subadditivity holds. So that was why I developed the Maximin method for proving things about holographic entanglement entropy. So that involves the Maximin formula. So that goes like this. Yes?
When is the set of external surfaces not discrete? In that case, the lower minimum exists?
Oh. I don't know any examples offhand where that happens. But I've never seen anyone try to prove it doesn't happen. Maybe there's a contradiction if you assume that there's a family of extremal surfaces that are infinitely close to each other. Maybe you could prove there's something, you could probably prove there's something bad about that. I just wanted to hedge my bets. So the Maximin formula involves a two-stage variation. So what we do first is we pick a Cauchy slice that passes through the boundary of R. So let's call this Cauchy slice sigma. So the first step is on each ADS Cauchy slice sigma, we find the minimum, the minimal area surface. Sometimes there are ties, like in the case of the phase transition, but if so, we'll just accept them both. So we find the minimum area surface that we could call min r comma sigma. And then for step 2, we vary sigma to maximize the minimum. To maximize the area of the, so okay, and this is called the maximum surface. Now, what properties does this have? One of them is that it, by construction, it's always minimal on some Cauchy slice sigma. The second thing is that we can prove that this surface, so when we vary this, we vary it to find, I'll call this capital M of R. We can always prove that MR, so we can prove that MR equals little mr on physical spacetimes, which are spacetimes that obey certain criteria I'll tell you about in a moment. And it makes it easier to prove these sorts of inequalities. So what I'm telling you is that there's a theorem that says that the maximum surface is equivalent to the Hrt surface on certain spacetimes that have good physical properties, and not generally equivalent otherwise, and that for this surface you can prove things like strong subadditivity more easily. Now, whether you want to use this all depends on what you want to do. If you wanted to calculate the location of the extremal surface for some specific boundary geometry, like in the homework problem I assigned you a while ago, then you would never ever want to use this maximum formula, which involves 2 steps, minimizing and maximizing over infinite, horrible infinite dimensional spaces. But if you want to prove things, then you probably want this, possibly. Yes?
Is it not always maximal on some surface? Or am I misunderstanding?
No, we're varying sigma so as to maximize the value of the minimum. So on the value sigma, on the sigma that I found it's always the minimal area. Yeah. The maximization is between sigmas. Now, maybe in some situations you might be able to prove its maximum on a certain kind of time-like surface. But okay. So what do we have to assume about the space-time for this to be equivalent? So I can tell you about the assumptions that I made in this paper, some of which may be not necessary, but so I'm assuming it's smooth and classical and asymptotically locally ADS, I'm assuming the null curvature condition, which says that the Ricci tensor, RAB, is greater than or equal to 0 for all points and all, oh, I forgot to contract this. VA, VB is greater than or equal to 0 for all points and all null vectors. V. So why is this important? It's because it's related to, if you apply the Einstein equation, then this is equivalent to the same statement for the stress energy tensor, and this is called the null energy condition and is satisfied by most reasonable classical matter fields. Although there's a whole conversation about how this is modified when you have quantum fields that has popped up in several talks. Let's just be classical for the moment. So this is physically required, and in fact, for most of the results for convenience, I like to assume the generic null curvature condition, which says, well, there's various ways to phrase it, but one version would just be to say that this is strictly greater than 0, so that I always have a little bit of matter energy focusing the geometry at any given place. So this is advantageous for some purposes, and at the end of the day, it's not really much of a restriction because any space-time that satisfies the null energy condition will be infinitesimally close to some other space-time that satisfies the null generic condition. So assuming continuity, anytime I prove any inequality using the generic condition, I can always say it's true even if I didn't have the generic condition at the possible price of having to replace a strict inequality like greater than with a weak inequality which is greater than or equal to. Does that make sense? So, and the other thing that one needs to assume is I assume the ADS version of global hyperbolicity. So global hyperbolicity is the statement that you would need to assume about the geometry to know that you have a well-defined wave propagation of like the Laplacian on that geometry. However, that's not the definition. The definition is a geometrical definition, and it has two parts. So the first part says that there's no closed causal curves. So I can't find a null surface or a light ray that goes in a circle back around to its original point. And so that would obviously violate causality and make there be unwell-defined propagation. But the second thing is that there are no boundaries, no non-space-like or null boundaries, no time-like boundaries, one might say. Or to be more precise, the way people phrase this is if I have 2 points, P and Q, and I take the past of P and I take the intersection of that with the future of Q, then this should be compact. So let's draw that as a picture. Suppose I had a boundary of like some naked singularity or something that was time-like, and I take the past and the future, then you see there's a boundary hole here. So that would say you don't have well-defined wave equation because you need a boundary condition at this singularity to say what happens. Now, hopefully, if I didn't say what I'm about to say, one of you would object and say, but wait a minute, ADS has a time-like boundary, so it's not globally hyperbolic. And the answer is yes, and that's why I said it has to be the ADS version of global hyperbolicity, which is just the same, except we say that the boundary of the ADS geometry is okay. Why is it okay? Well, we put a boundary condition there anyway. So it's, okay. So given these assumptions, it's equivalent. Now, I was planning to describe the proof that it's equivalent, but that will have to be for the next lecture because we're running short on time. So let me instead observe about this definition that in the literature you can find some stronger sounding forms of some more complex definitions of global hyperbolicity, but it was a few years ago proven to be that 1 and 2 is sufficient to get those stronger sounding definitions are actually equivalent. So I forget the name of the person who proved that, but this definition is much more convenient than ones that you might read in an old textbook somewhere. And so next time I will go into this maximum result, not so much because I want to brag about my own work, but because a lot of the intermediate steps are very useful geometrical theorems that I believe some of you will find useful for applications in completely different contexts. So that's what we'll do next time, and hopefully we'll also have time for the path integral derivation of the holographic entanglement entropy.
Questions?
Yes?
This procedure, point number 2 in this recipe, selects a particular sigma, right?
Almost. So not quite, because if you think about it, whichever sigma we pick, there's going to be lots of variations of this surface that are away from the minimum area surface that may not change it. So I would say it selects a class of sigmas that are all equally good in some sense.
Do they have, is there a way to classify, a characterization of these surfaces? Can you turn the problem into a characterization?
Well, it implicitly characterizes them, but generally for what I do with it, it's not very important because I just have to assume there's a surface that has this property. And in fact, there's a very large infinite dimensional class. Because if I don't change it, I could imagine that if I changed it enough, this is no longer the minimum area surface. But if I change it a little bit far from the surface, I'm not going to change whether it's minimum. And as a general matter, when there's like a tie between multiple choices, usually what I do is just say they're all equally good and not try to discriminate further. So whenever I say minimize, I really mean a minimal example, not a minimum, of which there can be only one. Yeah.
Which of these assumptions are necessary for the maximum formula to hold?
Well, none of them, I will get into this next time. But none of these assumptions are necessary to define it, but you need pretty much all of these for it to actually be equivalent to HRT. The ADS global hyperbolicity is, actually there's some caveats I haven't really put in here regarding the question of whether it exists in the first place. I'll deal with that in more detail next time. Yeah.
One more. Okay, let's thank again to Aron.